Fans. What would we do without them? Even before we figured out that air is a fluid, we've been pushing it around at our whimsy. And thanks to electric fans, things are better than ever. They keep us and our things cool by speeding up the transfer of heat energy. They make your voice all funny when you talk through them. And if they're old enough, they are a clear and present danger to anything with fingers. Yes, the world's a better place thanks to fans. Fans. It's what's for dinner. But the common electric fan has a, depending on who you ask, mildly perplexing to intensely irritating design quirk. You see, most fans run at multiple speeds, most commonly 3, and nearly all of them have a speed selector switch with the order of off, high, medium, low. Why are they in that order? It may seem more logical for the speed to increase, as after all, things like volume knobs and dimmer switches tend to increase intensity the more you turn it. But fans? They're like the opposite. Why? Well, there are 2 basic reasons for this. The first is that this is just how it is and we're all used to it by now, so why bother changing it? And the second, more real answer is that this protects the motor inside the fan and increases customer satisfaction by reducing the likelihood of a stall condition. What's a stall condition? I'm glad you asked! Electric motors are weird. I mean, they're also amazing and wonderful, but they're also weird. At their core, it's really just some sort of magnet that we figured out how to make go all spinny. Then we put some sort of output shaft on the spinny magnet and we can make other things spin, like paddles which push air forward and thus create a constant stream of moving air. Or the little dish at the bottom of your microwave, or a train, or a car, or really anything at all. But getting the magnet to spin isn't as easy as you might think. Obviously, we can create a magnetic field that attracts something to it. Coils of wire make excellent electromagnets. But we can't simply create a magnetic field around a magnet and get useful motion. Sure, it will attract the magnet to itself, but once it's done that, well, then it won't spin, will it? It'll just sort of move a bit and then get locked in place. So we need the magnetic field itself to spin. Then the magnet in the core of the motor is being attracted to a continuously moving target and not a stationary one. There are a whole bunch of ways we can do this, and we don't even need to use magnets at all. In fact, we usually don't. Instead, the spinny bit, which I should probably add is called the rotor, can itself be another electromagnet. Or, if we want to get real fancy, can be made of steel and copper, and thanks to our friend electromagnetic induction, fields from the stator induce currents in it, and it becomes its own electromagnet attracted to the very fields which created its attraction in the first place. And yes, I'm oversimplifying. So anyway, to make a motor spin, we need a rotor, which may or may not contain a permanent magnet somewhere, which is attracted to a spinning magnetic field induced by the stator which surrounds it. That's the stationary electromagnetic bit. Now, this is all well and good, except for one thing. Household electricity doesn't spin. It just pulses. 3-phase electricity does spin, though. Grid-scale electricity generation and transmission is done as 3-phase power. That's why you always see transmission lines in multiples of 3. We do this because thanks to math and stuff, it allows us to transmit more power with a given amount of conductive material. Going from 2 wires to 3 allows you to transmit triple the amount of energy, and that's economical right there. The 3 phases are staggered 120 degrees apart from one another. Each phase on its own is just pulsing on and off, but in sequence they chase each other, just like the lights on a movie theater's marquee. If your name is Tesla, or ironically Ferraris, no relation, and you design a motor with a 3-phase stator and ensure they're in the correct order, you'll get natural rotation of the field thanks to the chasing effect of the phases. Lots of big industrial motors are built like this, and so are the motors in modern electric cars. With a motor on the grid, it will have a fixed speed thanks to the fact that the electric grid itself has a fixed frequency. But in an electric vehicle, the motor is hooked up to some fancy power electronics which turn the DC power from the battery into 3-phase AC power at whatever frequency and voltages you like. This is called a variable frequency drive, and they're not exclusive to electric vehicles, and in fact in EVs they're usually not called that, but that's a story for another time. Wasn't this video about fans? Well, I promise. We're getting there. Three-phase power is generally not found in the domestic environment. The closest you'll typically get in the US anyway is in a situation like an apartment building, where the building has a three-phase supply, and there might be things like elevators or large HVAC units with three-phase motors in them, but you'll only have two of the three phases in your personal breaker panel, and large appliances like electric stoves will be put across two of them, giving you 208 volts rather than the standard 240. Our electrical system in the US is weird, but that's a story for another time. So anyway, with only a single phase, you ain't getting rotation. You're just getting power and thus a magnetic field, which pulses on and off, and changes polarity with each cycle. Now, you can design a motor to work with that just fine. The universal motor is one such design. Here, a commutator and brushes are used to provide its own spinning field by switching the polarity of that field as the rotor, which typically is itself also an electromagnet, spins, therefore always creating a traction in one rotational direction. They even work on DC power, which is why they're called universal. But the carbon brushes, which carry current through the commutator, wear out over time. They're not usually super efficient. They create a lot of electrical and often audible noise. There's usually some arcing going on, and so they're typically only used in certain applications which don't run them for long periods at a time, like power tools or food processors. For something like a fan, which may run for days at a time, you'll want to use an induction motor. These don't have brushes that wear and will generally last as long as their mechanical bearings do. And you can make an induction motor work with a field that isn't rotating, because the rotor itself rotates. Keep in mind that from a spinning motor's perspective, the stator is what's spinning. So the electromagnetic field itself is too, even if it's not rotating from our global perspective. But of course, when you first turn on the fan, it's not spinning, and this is bad. See, the amount of torque an induction motor produces is a function of its slip. Slip describes the difference in speed between the rotating magnetic field and the spinning rotor. The rotor actually has to be moving through the field produced in the stator in order for it to react against it and produce mechanical force. And this means that single-phase induction motors are not self-starting. If both the field and the rotor are stationary, no torque is produced. In contrast, a stopped three-phase induction motor will immediately produce torque when it receives power because the field is rotating around the stationary rotor, and that means that the rotor is consequently moving through it even when it's stopped. From a standstill, the rotation of the field around the rotor will induce the necessary currents in it for it to start moving, and will accelerate until it's almost, but not quite, to the same speed as the rotating field. It never reaches synchronous speed with the field because then it would not be slipping at all and no torque would be produced. And this is exactly the reason a single-phase induction motor cannot start itself. There is no slip when nothing's moving. So now you've got a problem. How do you get the rotor to start rotating? Well, you cheat and create your own rotation somehow. There are a ton of different ways to go about this. You can use capacitors, you can use shaded poles, you can use a separate out-of-phase start winding, which gives a temporary kickstart. You could just give it a push. The specifics don't really matter, but what does matter is that you've got to generate a rotating field, at least temporarily, to produce enough torque to get the motor going. After which point the rotor's movement relative to the stator produces the necessary currents within the rotor's windings to keep itself going, and we're happy. And yes, I am still oversimplifying. We'll talk about Fleming's rules and Lenz's laws when you're older. One of, if not the, simplest ways to create rotation with only one phase is with a shaded pole motor. Let's look at one. It's a good thing I still haven't put the selection accumulator back in the jukebox, because it's got one of these. Now, this is a C-frame motor. These look a lot like transformers and indeed operate a lot like transformers, but they're actually Decepticons. Instead of another coil on the other side of the iron core for converting voltages, it's got a squirrel cage rotor. This is the bit that has currents induced in itself, producing electromagnetic fields which react against the fields created in the stator, which in this type of motor is the hole in this side of the core, but that's not what's important right now. Instead, it's these little bits of copper. These are called shading coils, and their job is to react to the flux created by the field coil over here and slightly delay its phase in these two locations. Electromagnetism is weird and complicated, and I'm getting deeper than I need to really. as always, but here's the upshot. These coils break the uniformity of the magnetic field produced in the stator, causing a very slight delay in flux in these two locations, which will in effect produce a bit of rotation in the field overall thanks to that shifting in time. These shaded poles provide just enough rotation in the field to get the rotor spinning from a standstill, and once it has enough speed, the induction currents in the rotor become quite substantial as it moves through the bulk of the pulsing field, and now it really takes off. So what does this have to do with fans and their switches? Well, everything. You see, the shading coil isn't really that great of a way to start a motor. It works, but the amount of starting torque it creates is quite small. They are, after all, completely passive components, sort of stealing a bit of the output from the stator. That weak sauce starting force means that this style of motor is really only suitable for loads like, well, a fan, where the force required to start it spinning is relatively low, and the load increases as rotational speed does. To start, it really just has to overcome static friction, but once it's spinning, it can really induct. And that's the main reason that high is typically the first setting next to off. While a shaded coil motor isn't super great at producing starting force, it's cheap and entirely passive. You don't need a component like a capacitor or a centrifugal switch to disable a start winding. You just give it power and it goes. But the amount of starting torque you get depends on what speed the fan is set to. The different speed settings are usually accomplished with different windings within the motor that produce varying amounts of power, and thus torque. And since the shaded pole affects all the windings equally, on lower speeds you get proportionally less starting torque. Making the first selectable speed high will ensure that the motor will, at least briefly, produce the maximum starting torque it can whenever it's switched on. That way it's more likely to successfully start. This hand chopper is nearly 100 years old, and it too has its switch in the order of off, high, medium, low. Now, it's probably got a shaded pole induction motor. That design certainly isn't exclusive to C-frame motors, but this motor is literally an antique, and I would rather not take it apart to find out for sure. Anyway, since I can just easily reach out and grab the fan blades, I can demonstrate how weak the starting torque is. It's surprisingly easy to hold the blade back, even set to high. This little fan moves a lot of air on high, and that obviously produces much more force than it is exerting on my fingers right now. This is seriously much weaker than you might expect. Now, if I dared to reach in and grab the blade while it was spinning, I would regret it, but also I'd find it would be producing much more torque than it is right now. Because, well, that's just how induction motors work. But you don't want to find a motor in this stalled condition. Why? Well, because current is still flowing through the stator windings when it's stalled. I mean, you can hear it. And in fact, there's more current flowing through it right now than would be if it were spinning. This fan uses about 42 watts when it's on high, and right now with the motor stalled it's using more than 70. That's getting dissipated as heat in the motor's windings, and before too long it could burn itself up. If the fan switch were designed with low in the first position, you could turn on the fan and find that the blades didn't start spinning. This would not only be annoying, but could hurt the motor. And in a fan like this, potentially start a fire. Now, to be clear, modern fans are required to tolerate being stalled for indefinite periods of time without burning your house down. After all, you could have left it on low, had a power interruption, and not get the benefit of the start-in kick. New fans will either have some sort of thermal protection or simply have a stator design which can't possibly pass enough current through it to get dangerously hot. Still though, you don't want a stalled motor. It's bad, and also just annoying. Now I should add that it's not like most fans can't produce enough starting torque on low. If I have this set to low and then plug it in, it gets going just fine. But it doesn't hurt to play it safe. And fun fact, I have encountered a ceiling fan on a fan control which was in fact stalled on low. I had switched it on and you could hear it humming, but it wasn't turning. I needed to increase the speed to medium, which produced enough torque to get it spinning, and then I can move it back to low. And it turns out that these modern electronical smart fan controls I installed because I couldn't help myself are designed to prevent that very thing from happening by always initially switching the fan to high. This here is my biggest fan, and I last had it set to low, so when I turn it on, it will go back to that same setting. But for about 2 seconds, the fan control gives it full beans to make sure it starts spinning, and then it switches to low power. Pretty neat, huh? In fact, these fan controls are themselves pretty neat just because they're bypassing the fan's internal speed controls and creating its own. And I should also add that ceiling fans often use capacitors as part of the speed control schema. Really, there are just a gazillion types of electric motor out there, and you can lose your mind trying to keep track of all of them and the ways we control them, but that's a story for another time. Now, it could very easily be argued that this high comes first positioning isn't really required anymore. After all, how frequently would a fan motor stall anyway? At least one like this. And you could argue it was never required anyway. I mean, this thing's 100 years old and it starts fine even on low. And there could very well be fans that don't use shaded pole motors. In fact, there are certainly exceptions out there, and even fans which do in fact put low first. Whether that's because they use a different motor design or just because somebody did the math and realized we've been worried about a very unlikely thing is unclear. But one thing is certain. The fan switch isn't, or at least wasn't, designed like this just to annoy you. There is in fact a method behind this madness. When you take an already not great method of starting a motor and weaken it with lower power settings, it doesn't hurt to give it a kickstart first. Maybe at this point it's more tradition than it is actual need. As a matter of fact, I've had this very fan on a separate switch for years with it always set to low, and it never once stalled. It clearly produces enough torque on its own to get going in any speed. And it's almost a century old. But the fact that these modern fan controls always kick the fan on high from a stop is, I think, a sure sign that putting high first is very intentional. Besides, even if stalling weren't likely, well, how else are you supposed to know how many times you're going to need to pull the ceiling fan chain to get to the speed you want? There's something with the delivery of that line which I didn't particularly like. Did that say, I better re-record that because asked might have sounded a little different. The 3 phases are with a motor on the grid. I should silence that, shouldn't I? I should remember to do that before I start. Anyway, we'll be back. There's usually some arcing going on, and so they're typically not used in most. Only used, not used, only used. That's fine. That's fine. Just go ahead and that's fine. If I have this set to low and plug it in, but I need to turn the quarter in, are designed to prevent that very thing from happening.